Every industrial AI conversation eventually comes back to a few questions. Does the AI understand the plant, or is it only speaking fluent uncertainty? Does your AI system captures the memory of your veterans? Do the dashboards they come with provide explanations? Do the physics simulation models take plant reality into account? Before GenAI, agentic AI, root cause analysis, RCA, or optimization can be trusted, they need the operating memory of the plant, the people, the constraints, the timing, the logic, and the real trade-offs.
In power generation, the problem is not only whether megawatts exist on paper, it is whether they are dependable, dispatchable, and deliverable when the system needs them. The AI system the plant adopts and deploys, can its GenAI module cite plant evidence and not simply invent a fluent answer? The real gap is an operating twin that can rehearse derates, starts, fuel switching, grid constraints, and explain the evidence before dispatch decisions become real-world risk. Automotive and EV assembly lines are not just machines and robots. They are choreography, timing, buffers, quality gates, rework paths, and human judgment. Does the simulation foundation for AI takes into account, for example, tact, the production beat, or rhythm that helps a factory or process avoid producing too fast or too slowly relative to what customers actually need? The missing question is whether a new line, cell, or product variant can be rehearsed before capital is committed, and before an AI agent recommends changes that ignore the line's real constraints.
In food and beverage, quality often shows up first as operator instinct, a sound, a color, a viscosity change, or a pattern that no dashboard has fully captured. Is the AI platform grounded in plant reality, and thus can AI answer quality questions while respecting batch records, sanitation, recipe logic, and compliance? The market gap is an operating mirror that connects recipe, sanitation, packaging, cold chain, yield, compliance, and profit risk before a new SKU creates avoidable surprises. In pharmaceutical and biotech manufacturing, AI cannot simply be clever. It must be bounded, explainable, traceable, and respectful of SOPs, validation, and human approval. Therefore, the system must be able to determine which process steps are truly critical and who knows the conditions that make them drift. The real need is governed production context that helps teams rehearse scale-up, deviations, hold times, and documentation burden without turning AI into an uncontrolled shortcut.
With respect to oil, gas, refining, and petrochemicals manufacturing sectors, one operating decision can have cascading impact on yield, energy, emissions, corrosion, safety, and downstream unit behavior. A seasoned operator sees a tower, compressor, heater, or flare network as one story. Can AI see it too? In adopting and deploying AI, the focus should therefore be on whether AI can understand the plant as one connected operating story before it recommends an optimization that looks good on one screen but creates risk somewhere else.
In the manufacturing of chemicals and specialty materials, chemistry cannot be hallucinated, and process control cannot be guessed from generic patterns. An AI platform should allow new products routes to be rehearsed before real materials are committed and an operational de-risked path taken. What is missing is deterministic, governed AI grounded in recipes, pressures, temperatures, SOPs, control logic, safety boundaries, and behavior context. For the manufacturing of metals, steel, and heavy materials, experienced operators read furnace color, roll vibration, slab behavior, heat timing, and quality risk before a simple trend line moves. An AI-based platform must be able to reliably allow sequencing, scheduling, heat treatment, and rolling constraints to be tested using SME knowledge before any physical operational changes. The market gap is not another asset dashboard. It is an intelligence layer that understands the full line-wide choreography of heat, force, metallurgy, maintenance, and safety.
In pulp, paper, and packaging manufacturing, economics live in fiber, moisture, tension, speed, grade changes, waste, and conversion timing. Basis weight, moisture, speed, and waste should be simulated before physically switching grades, and the data be used to build models for AI to explain a defect across pulp, press, dryer, and coating. Therefore, the question is whether AI adopted can explain for your plant a defect across the connected paper machine, not just point to one signal after the cost has already been incurred. In semiconductor and electronics manufacturing, tiny deviations can cascade into major yield loss, IP exposure, and expensive uncertainty. Therefore, when adopting an AI platform, one should determine first if a platform can model product, tool, or process step changes before yield is placed at risk. The required AI platform should have a layer that is protected with plant-specific intelligence that connects tools, recipes, routes, clean room discipline, tolerances, and constraints before AI becomes a risk multiplier.
Aligned to power generation, when dealing with utilities and grid assets, available power, dispatchable power, and deliverable power are not the same thing. It is essential that an adopted AI platform can support decisions within context and without hallucinating, and thus wanting to control based on what it understands from outside of production context. The market gap is explainable intelligence that connects generation, storage, renewables, outages, grid limits, assets, and human authority, without pretending AI controls what it only understands.
In the market today, there are excellent point solutions such as physics simulators, historians, IIoT platforms, OEM tools, dashboards, RAG layers, optimization engines, and GenAI assistants. So the question becomes, what is missing? The answer is a structured operating scaffold that is built based on process areas, machines, sensors, actuators, PLC-like logic, behavior profiles, SKUs, scenarios, and SME knowledge. Across all the industries we have just looked at, the gap is not more AI. The gap is operating reality intelligence that AI can safely reason over. Before AI tells the plant what to do, make it understand how the plant actually runs. TAAIB vCPPS platform fills that gap by modeling the operation, capturing knowledge, running scenarios, and governing intelligence before AI tells the plant what to do. TAAIB vCPPS platform adopts a creep to walk to run approach with its 4 core layers. 1. Simulation scaffolding. 2. Smart manufacturing vCPPS. 3. Intelligence layer. And 4. An optional machine I/O switch layer. Why does this creep to walk to run adoption approach matters? Because it is no touch first. It inherently provides lower risk, better ROI path, governed AI, tacit knowledge preservation, and decisions grounded in how the plant actually runs. What are the objections to TAAIB vCPPS platform adoption that TAAIB typically hears from potential clients? The first objection: our team is already overloaded. Who has time for another AI pilot? TAAIB acknowledges that is a fair objection. Plant teams are overloaded, and nobody wants another pilot that steals SME time while the real work piles up. The answer is proof velocity. TAAIB does the concierge scaffolding. SMEs validate in focused sessions, and the pilot is designed to produce evidence without months of workshops. The second objection, which is manifested as a concern: no integration sounds safe, but how can it be real? The second objection is also fair. If nothing connects to the historian, MES, PLCs, or live tags, how can the model be real? The answer to this second objection is that, in the creep and walk phases, these are no touch by design. First, model topology, behavior, constraints, logic, and SME knowledge. Then, in the run phase, optionally validate one machine at a time in read-only run mode. The third objection: what do we get before the hard KPI moves? This third objection speaks to the issue of whether TAAIB vCPPS platform is a science project. TAAIB acknowledges that executives do not want another science project. They want an artifact that helps a decision move forward. That is why success with the creep, walk, run approach is a phased one. First, validated scaffolding, then scenario replay, then forecast, RCA, optimization, and governed GenAI decision support. The fourth objection: is this just another pilot that dies in pilot purgatory? Here again, TAAIB recognizes that pilot fatigue is real because many dashboards, demos, and AI proofs never become part of operating routine. However, TAAIB vCPPS platform addresses pilot fatigue by starting with ownership, success gates, reusable behavior libraries, a scale plan, and a transparent path beyond the pilot. The fifth and final objection: is TAAIB vCPPS platform really different, or are we just hearing digital twin language again? The final objection as a question is the most important one. Is TAAIB vCPPS platform truly different, or just another digital twin message wrapped in AI language? The fair answer is simple. TAAIB does not ask for a client to believe the claim blindly. Rather, TAAIB asks, run one bounded pilot, model it, validate it, replay it, and then decide based on proof.
Across every industry shown, the question is not whether AI is exciting. It is whether AI can understand the real plant, answer the real objections, and support decisions without creating new operational risk. That is where TAAIB vCPPS platform fits. Whatever the industry, it helps model, simulate, validate, and govern operating reality, so teams can move from skepticism and pilot hesitation to confident, explainable, plant-grounded action.